increased loading of nutrients and sediment, possibly fueling more eutrophy and drawing down oxygen levels. And then there's the direct effects of increasing temperature on bay oxygen levels as well. So that can be through decreased solubility and increased remineralization rates. And then lastly, there's the impact of sea level rise, which can potentially bring more oxygenated ocean water into the bay, but could also strengthen the picnic line and decrease the vertical transport from surface to the bottom. But for the purposes of my talk today, I'll really be focusing on just the impacts of watershed changes on bay hypoxia, because it's really all that environmental managers can have some sort of control over to help improve oxygen levels. They can't control the air temperature over the bay, nor can they control the rate of sea level rise at the mouth. So when we think about climate scenarios that are used to force future estimates of hypoxia, there are a number of sources of uncertainty that are implicitly built into these climate projections. The first is your choice of global climate model, a multitude of which are shown here in this upper left oval, and selecting which ones you like to use to reduce the computational burden is a pretty non-trivial task. And then these GCMs, one of which that we use here, are very coarsely spatially resolved, so they need to be downscaled through either a statistical method or a regional climate model. In our work, we use two different downscaling methodologies, so they're actually applicable to these regional applications. And those gives us estimates of temperature and precipitation, which are not fed into your estuarine model, but are instead used to directly modify the inputs to two independently developed watershed models. The first over here, phase 6, is an EPA, Environmental Protection Agency regulatory model that is used by environmental managers and localities and states to apportion estimates of nitrogen reductions throughout the watershed. And the other, this dynamic land ecosystem model, or DLEM, is run by our partners at Auburn University in order to answer different scientific questions and is a more process-based model. And with these climate scenario inputs, they provide us with estimates of changes to discharge nutrient loading, which when fed into an estuarine model can give us estimates of hypoxia. And so the experimental setup for our work was to compare 5 different GCMs, are shown here, and then both of them will be downscaled with the MACA methodology and the BCSD downscaling methodology, and then forced through these 2 independent watershed models for a total of 20 possible climate scenarios. And as I mentioned, selecting which GCMs you would like to use is a fairly non-trivial process. So we are looking at estimates of change by mid-century compared to the 1990s, which is important for management purposes here in the Chesapeake Bay. And what I'm showing in this plot are the changes in warmer month temperature against November to June precipitation, because these time periods have been found to be most highly correlated with changes to hypoxia in the current period. And what's often done is perhaps selecting just a center model, maybe a cool center and warm, but what we do in this work is mathematically draw a kind of lasso around this distribution to get a set of 5 GCMs. One is the center of this distribution. Another is cool, dry, warm, wet, warm, dry, and then cool, wet. And I should also note that these are all warmer than baseline period as we'd expect. And almost all of them are wetter than the reference period as well. It's just relative to their cooler, warm, or dry or wet relative to the center model. So we have 5 GCMs selected for our climate scenarios that are downscaled. And then we apply these climate inputs to an estuarine model, a formulation of the regional ocean modeling system called Chesron's ECB. This is coupled to an estuarine carbon biogeochemistry component. This is a 3-dimensional model with 20 depth levels and gives us daily outputs, both past and future scenarios of changes to hydrodynamics and biogeochemistry. And it's been pretty thoroughly evaluated over the last 8 years or so against these monitoring stations, over which there's over a 30-year record. And we have inputs from hindcast weather data, a reanalysis product, coastal fluxes at the ocean boundary, and riverine inputs from these 2 watershed models that I mentioned previously, the regulatory phase 6 model and the more process-based scientific DLEM watershed model. And just as a reminder, I'm only going to be mentioning the effects from riverine inputs, so excluding the direct impacts of changing atmospheric temperature on the bay and what's going on at the ocean boundary as well. So to get right into the results, here I'm showing the change in hypoxia over a future 10-year period from these 5 GCMs, so just the change due to your choice of global climate model. And the y-axis is showing the change in annual hypoxic volume for dissolved oxygen levels less than 2 milligrams per liter in percent. And we see right away that there's pretty substantial variability in changes of hypoxia due to your choice global climate model. But generally, wetter GCMs produce more hypoxia than drier GCMs because of increased runoff and nutrient loading. But this is just for a single downscaling method and watershed model. So if we were to compare all of our 20 scenarios, we can see in this slide that we have our 2 rows of watershed models and 2 columns of downscaling methods, and it's a whole lot of variability. But overall, there are some key takeaways that we can gather. And the first is that 4 out of 5 of these scenarios project an increase in average hypoxia conditions. And while downscaling might be important to some, for example, I'll point out here with the same watershed model and the same GCM here, this cool dry produces a negative change in hypoxia for one, but a positive change for a different downscaling methodology in another. So completely opposite sign just based on your choice of downscaling method. But that's not as common as others. It's not quite as variable as your choice of GCM. And then on average, the DLEM watershed model gives us more hypoxia than phase 6, but it's more variable. That's largely due to the way that they process nitrogen in the soils in DLEM versus phase 6. On this next plot here, I'm showing the exact same data on the previous slide, but just crunched into both a PDF and a CDF curve. So on the left, we have the change in annual hypoxic volume in this unit of kilometer cube days, or the total amount of volume that's affected by low oxygen waters over the course of a given year. And we see that there's a nice distribution that shows us a median increase of about 40 kilometer cube days. And when plotted as this cumulative density function, we see that there's about a 70% chance of increasing hypoxia as opposed to decreasing hypoxia. But as I mentioned earlier, we've chosen these GCMs to represent the maximum sort of level of variability to capture the full range of outcomes. So this might get may become a narrower, tighter distribution if you were to add more GCMs. And then lastly, I've kind of said these things have more variance or one or another, but we sought to quantify this better by using a NOVA approach, which partitions the variance of hypoxia for these multiple effects, your choice of global climate model, downscaling method, or the watershed model. And when I talk about how cumulative uncertainty accounts for and grows with each of these effects, and define that uncertainty as the fractional contribution of each of these individual effects to the total variance. So altogether for your uncertainty and hypoxia in the future, we see right away that all of these factors in setting up a climate scenario are important when projecting future hypoxia in this coastal zone. Selecting just a single GCM or downscaling method and excluding your watershed model could leave you missing up a quarter up to half of the possible range of outcomes, which I think is fairly high. But to now, I haven't mentioned the effects of the projections of hypoxia and uncertainty. These are all scenarios without the effect of management conditions. And when I include the impact of management actions, this is that same curve that I showed previously, but it seems much steeper because it now includes the effect of management as well, which substantially reduces the likelihood of any hypoxia in the future from watershed impacts due to climate change. In fact, we see that the reduction in nutrient inputs is projected to decrease average hypoxia levels by approximately half compared to the reference scenario. So these are fairly small changes overall with high levels of uncertainty due to the way that these different climate scenario setups process the inputs, but with the effective management actions, we see that it's a much more substantial change in helping to improve water quality, increase oxygen levels in the future. So in conclusion, if we only consider the impacts of climate change on river inputs and how that affects hypoxia, we see that the choice of GCM, downscaling method, and watershed model all contribute to uncertainty and hypoxia projections. And that while we have a likelier increase in nutrient loadings and hypoxia, about 70% chance without management actions, once you incorporate those and assume that they're met, which there are some caveats there and how effective they'll continue to be in the future, essentially the increase in hypoxia due to watershed impacts is entirely mitigated by planned nutrient reductions. And if you're interested in more of this work related to how we plan to look at this in the future with direct impacts in the estuary, you should check out my colleague Ellen Hawes' poster tomorrow. He's there in person for more information. Thank you.
So we're holding to time. We could take one short question. Maybe Andreas?
Thanks. Excellent talk. Question, how large do you think is the uncertainty due to biological or biochemical processes that may change under global warming or with sort of quality of organic matter, C/N ratios, nitrogen fixation, and benthic processes?
I think that's a large source of uncertainty as well. We meant originally to compare this against another estuarine model as well, and you could compare the different parameterizations of those two. That hasn't happened yet for this work. So I think it could contribute quite substantially, but again, this work was primarily focused on what environmental managers can do to reduce nutrient loads. I think even with possible changes to microbial processes with increasing water temperatures and changes to circulation from sea level rise, the effect of these management actions should still be fairly substantial to help mitigate a lot of those effects.
Okay, thank you, Kyle. So our last speaker for this session is Elizabeth Dusky, and full disclosure, she is a postdoc working with me and my colleagues in Sweden. She is in Ohio right now, and the title of her talk is Evaluating Potential Lost Yield of Eastern Baltic Cod Due to Deoxygenation. So it's coming right up.
All right, I think I have control here. So hello, everyone. Hello from the great state of Ohio. I'm so pleased to be here with you remotely, and super grateful to the organizers for working so hard to integrate this conference. So my name is Liz Dusky, as stated. I'm a postdoc with SLU Aqua in Sweden and SUNY ESF in New York. And I'll be discussing some work that I've done attempting to characterize lost yield of cod due to hypoxia. I'm presenting this work on behalf of myself and my supervisors and colleagues, Nick Cassini, Karin Lindberg, who's present, of course, and Anna Gordmark. I've begun with this striking image on the right here of a bloom in the Baltic Sea, something with which us and also the world at large, I think, are becoming increasingly familiar. These blooms are, of course, one of the major causes of deoxygenation in the Baltic Sea. Just waiting for slide transition here.
So maybe try to switch with the rows on your computer or by clicking on it. Okay.
Okay. All right, here we go. So this graph here on the right is another with which many of us may be very familiar. This is a time series contrasting cod spawning stock biomass, or SSB, with fishing mortality through the past several decades. So generally, you can see that these are strongly negatively correlated throughout the time series. However, in recent years, SSB continues to decline despite declines in fishing mortality. Studies on individual fish, many of them incidentally of which are on cod, point to a few major sources of potential decline. These include direct physiological stressors, changes in habitat use, direct mortality exposure, to extremely low oxygen, and as well as toxins and low prey availability. So declining oxygen leading to hypoxia in the Baltic Sea has several causes. The Baltic Sea is actually naturally inclined towards low oxygen. It experiences permanent stratification due to the presence of a strong halocline. Bottom topography also resists circulation of waters throughout the system, which in other systems works to replenish low oxygen. And of course, there are the anthropogenic causes, including high nutrient loading. This on the left here is yet another familiar image, I think, and perhaps a bit more dramatic, displaying the consequences of said eutrophication. The Baltic has also experienced declining inflows of oxygenated waters, and as well as rising temperatures. All right, so these here are results of a model of benthic and pelagic oxygen in the Baltic Sea. The benthic habitat, which is the solid line at the bottom, averages over the Celtic Sea in the bottom 10 meters. The pelagic habitat, by contrast, averages over the same region at around 10 to 40 meters. You can note the major Baltic inflow during the late 1980s and early 1990s, and of course the subsequent decline. So during the same time period, the condition of cod has declined quite steeply. This is a figure from the 2020 stock assessment showing declining Fulton's condition factor, which is a measure of weight as a fraction of length. So larger numbers indicate more weight relative to the cube of length. If you'd like to imagine a fish as a cube, which we modelers very often do, and thus a chubbier and healthier fish. This becomes more impactful, I think, when we take a look at some of the fish themselves. So this fish on the left here comes from a more oxygenated habitat, whereas the so-called necktie cod in the center here comes from a deoxygenated environment. This study that's cited down here at the bottom used otolith microchemistry to confirm a linkage between this worsening condition seen here and exposure to hypoxic waters in the Baltic. So there are, of course, a plethora of super interesting questions we can ask here, and we have asked a few, shown in gray. These first three, how observed dynamics emerge from individual fish respond to hypoxia, which of these pathways are most critical, and the consequences of these pathways for continued declines in oxygen are addressed on a poster that these same authors, including myself, have put together for the poster session. So keep an eye out for that. In this study that I'm discussing here, we use the same modeling framework to ask the following questions, shown in red. So how do characteristics of yield respond in more ideal historical relative to more recent conditions? And how do different pathways by which oxygen impacts individuals and their resources interact to produce estimated losses in yield? All right, so as a bit of background to orient ourselves, we explored the relevance of several pathways as drivers of observed declines in SSB yield and growth of Eastern Baltic cod as members of a community of commercially important fish species using a multi-species size spectrum model. So in addition to cod, these fish include a benthic competitor, the European and the Baltic flounders, as well as two pelagic clupeids, the herring and the sprat, as well as their benthic and pelagic food sources, represented here as a bitty plankton and an isopod. So the model that we've built follows individuals of each species for recruitment through death. So individuals acquire energy by eating some combination of the background resources shown here, depending on their habitat preference, as well as other fish species in the model according to weight ratio and species-based preferences. So other portions of the model include a stock recruitment relationship, which guides reproduction, and standard models of fishing selectivity. These processes are all built into the standard model structure in the R package MISR from the get-go. However, we added scaling components, which appear in this figure here in blue. These guide increase increases in metabolic costs with declining oxygen and declines in several other physiological and behavioral processes. So as I mentioned just a moment ago, the species in this model are cod, flounder, sprat, and herring in the Baltic, and we have the two resource spectra. There were some vaguely similar drawings on the previous slide, but I think my artistry is questionable at best. So here's some nice live pictures with which to ground ourselves. Right now, to summarize our work relating to the model that we're using, we categorize the impacts of deoxygenation as declines in the carrying capacity of benthic resources, declines in benthic occupancy of cod, increasing mortality due to exposure and physiological impacts, including increases in metabolic costs, declines in feeding and assimilation efficiency, and survival of eggs. We ran all possible combinations of these four pathways, including one with no scaling and all scaling, in order to determine which combination best represented observed dynamics of growth, mass, and yield in this community. The best model, shown here with this red square here, included scaling of benthic resource carrying capacity, as well as benthic occupancy of cod. So this here is a snapshot of these model results. We're looking at estimated SSB on the left and yield on the right during the calibration period, which is shaded in gray, and a projection period follows. Generally, you can see the model is decently capable of following observed trends in SSB and yield. For cod in particular, estimates are usually worse for flounder, but these data are more or less guesstimates, and so we're not quite so concerned about that. What we take from these time series here is that the model can be a useful tool for completing just this kind of yield analysis, not in absolute terms and in relative terms. So now the meat of our current analysis involved three steps. First, we acquired historic estimates of oxygen in the Baltic Sea. Then we used the best model, in this case, the very unfortunately designated BO model, to contrast projections with both historic and more recent oxygen levels. Finally, we also ran the component models, one with only B or benthic resource carrying capacity scaling, and another with only O or cod benthic occupancy scaling. This final point can help us determine how these two impacts of deoxygenation interact to lead to projected changes. So this is the first part. The oxygen model runs separately from the years 1958 through 1979 and 1980 through 2019. The data arise from the shark web system. The benthic oxygen is fairly steady around 2 milliliters per liter, which coincidentally is also the commonly cited hypoxia threshold. Oxygen rises in 1980 and then falls after 1990. Note that these are means for data collected in the entire central Baltic Sea. All right, so here's the second step. In this and the following step, we used average fishing mortality through the 1991 through 2000 calibration period. This graphic contrasts total yield for all species during the historic period in a dark shade of blue and the modern period in a light shade. In the BO model, declines in growth caused by declining food availability are offset relative to the B model by moving to the pelagic habitat where sprat and herring are available for consumption. Accounting only for declines in benthic resources leads to extremely sharp declines in cod, whereas accounting for changes in cod occupancy in the benthic environment leads to a projection even of slight increases in biomass as well as yield. So note that in reality, the index of benthic occupancy declines and then rises, which you can see here, declines during the calibration period and then rises, seen in these blue triangles. So that is, cod have actually moved up in the water column in the past, but are since reoccupying deeper waters, but likely into oxygenated refugia. This index is derived from a ratio of benthic to pelagic CPUE. So in general, this calls for careful accounting of spatial occupancy, both vertically and horizontally, so to speak. All right, so next we examine the size composition of the yield in each scenario. In general, declining benthic food in response to declining oxygen results in a shift to smaller cod on average in yield, as seen on the left here. Changes in occupancy alone do not cause noticeable shifts in the yield beyond slightly more yield and lower oxygen due to access to additional fish resources. On the other hand, declines in benthic food without the ability to escape results in slightly smaller cod and significantly less tonnage overall. So as for changes in growth in each scenario, the changes in these drawings here, the vertical thickness of said iffy drawings corresponds to changes in mean weight of the catch. So declines are steeper when benthic food declines, but no escape is available. In general, changing food availability drives changes in growth, which leads to skinny cod, which is what we observe. Changes in habitat occupancy modulate this response somewhat, but cannot fully compensate because of a mismatch between food requirements and food availability. So to answer our questions, how do yield characteristics change and deteriorating relative to more ideal conditions? In this particular scenario, total yield of cod declines by about 14%, or thinking about it from the reverse direction, yield could have been 40% more in more pleasant oxygen conditions. Furthermore, mean weight of cod in the catch declines by about 20%, and maximum weight of older individuals also declines by about 25%. Or again, cod could be much larger in more ideal conditions. So also the pathways we've identified as major drivers of this fish community's response to deoxygenation interact in really interesting ways. So the loss of benthic food drives the shrinking of cod, but changes in habitat use mitigate this somewhat, and more so for overall yield. In addition to total declines, the body size also declines, which can lead to additional losses in value, which can exceed total loss. So this is an exploratory analysis, which of course relies on the assumptions baked into the model structure, but it has some interesting implications for management and some potential economic considerations as well. So on that note, I'd like to conclude and thank current and previous members of my lab who allowed me to bounce ideas off of them. And also I'd like to thank the group, which are folks who all innovate with these types of size spectrum models in various fascinating ways, as well as our affiliates. So with that, I can take some questions perhaps.
Thank you, Liz. I think because we're running so late, I'm going to hold the questions and we're going to move along, but Liz will be here virtually all week, so you can talk to her through Padlet, I think.
Yes.
But now I'm going to turn the mic over to Lisa Levin.
I'm going to set your phone. No. Okay, I'm going to invite the panel members to please come up and take a seat, and I'll be introducing you. Everybody knows who they are. A couple people are online as well. This way. Like this, and then, okay, let's give them the microphone. Everybody gets to share a phone. Okay, this is our Oxygen Science to Policy panel. And we're delighted to have 6 esteemed guests to talk to us about their policy experiences. I think I'll just hold this. And I'm going to introduce them. I think 4 of you are here and 2 are online. Okay, so we have with us, you can raise your hand, Sheila Hammonds, who is the Executive Director of the European European Marine Board, and she's a professor in ecosystem modeling at the Scottish Association for Marine Science and the University of the Highlands and Islands in Scotland. There she is. I'm just going to go in the order I have. So online, we have Julie Pullen, who's a physical oceanographer, a climate technical professional and former ocean engineering professor, and her expertise is in climate, weather, and hydroscience. And she's participated in a whole series of climate reports and is on the council and executive committee of the American Meteorological Association. Here we have Andreea Stracinescu, sorry if I don't say it correctly. She's head of the Unit of Maritime Innovation, Marine Knowledge and Investment in the Directorate General for Maritime Affairs and Fisheries. And this organization provides policy input to Horizon Europe. We have Torsten Kiefer here in front of us, as he's director of the Joint Programming Initiative on Healthy and Productive Seas and Oceans. And is also a researcher in paleoceanography who's facilitated many international programs. We have Siggy Gruber online. There she is. And she is currently heading the newly established Marine Resources Unit in the Directorate General for, I might be wrong there, she's retired. Okay, she's the active senior advisor for the European Commission, correct? And, but has a long history with the European Commission, has worked in education and training and research career sector and innovative partnership sectors and so on. And then last but definitely not least, we have Irina Makarenko, who is the Pollution Monitoring and Assessment Officer of the Black Sea Commission Permanent Secretariat, and she permanently served as the Ukraine mission to EU, and is also a member of the pool of experts for the World Ocean Assessment. All right, well, thank you all for joining us online and in person. I'm going to be asking each a question, and then we'll see how the time is to engage the audience. We only have 45 minutes, so now probably 40 minutes. And I'm going to start with Sheila and ask you if you believe there's a need to link marine and freshwater oxygen management communities, particularly at the land-sea interface, and how you think scientists could play a role.
Thanks. Is it on?
Yes.
Okay. Yeah.
Can everybody hear?
Yeah.
Thumbs up.
Good.
Yep.
So yes, indeed, the question is, how do we need to link freshwater and marine? I think for sure, as we've heard this morning, there's quite a big impact from riverine runoff on anoxia, hypoxia. So indeed, we wouldn't be able to manage the coastal zone very well if we didn't have the inputs from the fresh water. So I think there's definitely a need for that. And at the European level, for the Europeans in the room and online, of course, the EU has just brought out the mission, which I won't talk much about because I think Andrea and Ziggy will talk about, but they specifically link freshwater and marine. And I think it's for sure an important thing to do. So I'll leave it at that. Thanks.
Thank you. Okay, I'm going to go to Siggy Gruber next, and we can't pass the microphone to you, but somebody in IT can. Do you think there is a place for national, regional, or global alliances in the Atlantic or elsewhere to address ocean deoxygenation? And how can scientists contribute?
Hello to everyone. I hope you can hear me well. Can you hear me? Good. So thank you for inviting me to share some of my thoughts. Of course, I think this is a non-question, Lisa. Of course, there is a place for really in the different alliances, in the Atlantic one, but also in other alliances. If you look at the Atlantic one, there have been a lot of activities and projects as well, targeting what you are discussing, the Ceres project, which is finished, the Triatlas one, which is ongoing. Many of the Marie Sklodowska-Curie activities, actually, we have a whole list that if anyone is interested, we can share it. So I think it is really to look into what is this collaborative advantage in joining up in an alliance? Is it for creating a level playing field, for creating trust, for pooling, aligning resources, for using and combining really the diversity of expertise? I think these are all very, very valid assets that need to be fostered. And of course, they will be fostered in future as well within the ocean mission. And I will talk afterwards. First, Andrea will talk about the mission. Thank you.
Thank you. Andrea, you're next. How important is it for stakeholders of the blue economy to understand ocean and aquatic deoxygenation? And what do you think the most effective methods are for making that communication?
Thank you very much. I think a lot are to be said, because what we are doing, first of all, is we work a lot on the other way around, I would say. We provided a policy for science, and especially with EMONET, we offer to all the scientists data coming across different institutes in order to develop their work. Blue economy is a concept that with the communication from last year, it showed towards what we are going in terms of decarbonization and in terms, of course, of meeting all the other policy objectives as formulated in the European Union Green Deal. Now, we have to see for the future, and I think probably this is a challenge that is coming at the level of the community, how we are going to communicate the importance of all the work, including the oxygenation. Probably when you speak about the ocean and you ask everybody in the street, the first thing that comes to their head is the plastic, because we were all of us exposed at a lot of images and communication that really made probably from the youngest to the oldest to say plastic is a problem. We saw birds that were fed with a lot of plastic. We saw turtles that were blocked in fishing nets. Now the challenge is how we communicate about other problems. So I think it's extremely important that the community needs to find as way, I would say, good and very well communicators, very well porte-parole, in order to bring this importance on the table of the politicians. Because we arrive at the point where, of course, we know very well that policy is developed based on science, based on a lot of work, but policy is developed as well based on the urgency that is communicated. So it's quite important how we are communicating this urgency, and for this we need to work together.
Thank you. I'm wondering if we need to have a image contest for the best way to communicate ocean deoxygenation. Yep. Irina, I'm going to come to you next. How do you see Black Sea management happening with respect to oxygen in the future?
Thank you very much, first of all, for the invitation to be given the floor also, especially within this session. As you may know, the Black Seas is the most anoxic body, and also the organization that I represent is actually trying for more than 30 years now to link somehow the science and policy. So of course, as this topic is very hot on our agenda for many years, and I wanted to thank Maria Laura, who is always contributing to a dedicated chapter on hypoxia of our State of Environment report. So I have a long list of activities that we have been doing, but to summarize them, and I may always provide you with details, but I think that the most important that we should do now is to harmonize our efforts, because all of us are doing and dealing but still, I think that we have. So in the Black Sea, of course, there are many challenges, especially right now. All of you know what is happening, and we will be also trying to address these challenges in the nearest future. For the moment, we have many different tools, many different reports. We collect annual reporting from all the Black Sea riparian countries. But if I speak about the problematic things, is always some lack of will sometimes the lack of information. Sometimes we speak different languages with, for instance, different conventions or our partners. And for that, we are doing so many efforts, and we created groups with Danube, because you know that Danube is a big contributor to the Black Sea. And one of our 4 main goals of our convention is to reduce eutrophication. So we have been dealing with all these issues from different sides. And thank you once again for inviting me. And it's a pleasure to see so many people interested in this particular issue. Thank you.
Thank you very much. Okay. I'm going to go to Torsten next, but I haven't forgot about you, Julie. You're after. So Torsten, what are some of the mechanisms or vehicles that you believe enable scientists to promote the deoxygenation topic at the science policy interface and also to funders?
Yeah, okay, so thanks for the question. It's mechanisms and vehicles sounds as if there was this one recipe to success, and I think there isn't. I think the process of how policy priorities develop, I'm still in the process of trying to understand. I think it's really a process, not necessarily chaotic, but it's a very organic process, I would say. Therefore, you bring the topic into the process if you think it is really important and should be addressed beyond just the scientific community. So how to? I mean, one thing clearly, you need to strike somehow the chord of interest of the policy makers, obviously, and there probably many will. Yeah, a lot of the policy is done in countries, and they have a bit of a national perspective, so they will be interested what is happening off their coast. Therefore, the global perspective that we saw a lot of this morning is super interesting. I'm sure it's also very relevant, but I would say it's good to connect that also with the local zooming in, and that, for example, that can then relate to the Black Sea, to the Baltic Sea, and we've seen also some of that. Yeah, ideally, both the open ocean and the regional sea and coastal areas can be connected in an agenda. Maybe I'm from JPA Oceans, and so that's a joint programming initiative, a pan-European one on ocean matters, and so we have obviously a European perspective, but as a very concrete offer, I would like to put out that we are now in a process of actually opening an online portal where community can bring to the attention of the country representatives topics that they think are of interest, of importance. That doesn't mean that it's picked up or anything, but it's a way of kind of formally bringing ideas into the system. And even if then JPA Oceans doesn't pick it up, and there's absolutely no promise, no guarantee that it is picked up, but somehow once it's in the system, there's a bit of a domino and a self-perpetuating effect. How then a topic might float to the top, and suddenly it maybe has this popularity as ocean acidification, which I sensed was a bit of a kind of the gold standard.
Great, thank you. And Julie, can you tell us what opportunities exist for scientists to engage in outreach and policy in your areas of study?
Sure. Thank you for that. Can everyone hear me all right? Okay, good. I'm really pleased to join you today. I'm really struck by the power of this global community that you've convened here. Though I'm from you in terms of my scientific background in air-sea interaction, observing and modeling, I'm not actually currently fully among you, either in person, unfortunately. I'm I'm here from New York currently, but also in terms of the arenas that I operate in. So most recently, I was with a startup, a venture capital-based startup that did climate risk analytics. And I left that last month in order to focus more directly on ocean climate solutions and investing in that space. My purpose is to activate the philanthropic and private sectors to support and catalyze science to action, and I'm particularly compelled by deoxygenation. I provided philanthropic support to this conference through COROA, which stands for Carbon Oxygen Restoration of the Ocean and Atmosphere. And you have my commitment to continue to support this global community to be able to accelerate the recognition of deoxygenation and the solution set around that, and in particularly the science to action piece of it. So to directly address your question, I think that there is extraordinary opportunity to work with companies who have already made strong commitments around net zero to align with the Paris Accord, but to work with them to up their ambition, and in particular to ask them to commit to threshold-based targets along the lines of what Erica Farrar was mentioning to get deoxygenation recognized as a planetary boundary, and aquatic oxygen metrics along those lines. I think that this is really compelling because the companies I engage with, large companies that I engage with really have an appetite to do more. They just don't always know the directions that are most important in terms of the science. So that connection between the science and commitments on the corporate side in terms of their policies around climate action, I think is a really important lever for this community. And happy to share more in the discussion part or be engaged with you all individually if you want to reach out to me. Thank you for.
Thank you. I think maybe we'll have to get you to send us a list of those companies and maybe share with the science community here. Okay. Well, I have more questions for these guys, but this is supposed to be an interactive panel. So I need Marie-Laure to tell me how long we have until 4 o'clock, is that right? So we have another 20 minutes approximately or less. And I do want to make sure that I have one round with everybody, a very brief action item round, but let's just see, does the audience here or online have any questions for our panelists? And can somebody check online for me? We can't see the chat to see if there are any questions there, but anybody up here? You're gonna have to wave your hand if you do. Okay, Denise.
I guess this is a question for whoever would like to answer it. We have talked a lot about the need to really focus very strongly on deoxygenation because it tends to get lost in the discussions of ocean problems. And at the same time, we've also talked about the issue of multiple stressors, interactions with oxygen with other problems, and just the overwhelming list of issues competing against each other to achieve a healthy ocean. And I guess I'm just curious what you think is a more effective way of addressing the issue. Anyone?
Okay, we're going to need the microphone here. I'd like, any panelists want to take this? Oh, you have a microphone. I'm sorry.
One.
Okay.
Denise, that's a really difficult question because it depends on who you ask. I think we have to be honest to say all of these things are important, and if you only look at one thing, you will miss out on the other things. Just like if you only do stock assessment of one species, you'll miss out all the impacts of all their food and their predators. It's the same thing. So you need a holistic approach, and we have to make it clear to policymakers and to the public that it's not only about about plastics, it's not only about temperature, it's about all of these things. And if you miss out one, you might actually not be able to know what's coming down the line for you. So I think we really need to get that communication out better. I don't know if anybody else has.
Online, anybody want to answer that? Siggy? That's it.
Yeah, thank you. Thank you for this question. Indeed, I fully agree with what was said. It's the call of urgency. It is really how can we help now ocean deoxygenation, how reduce it and work simultaneously on all these different issues. But one issue, it came across this morning, Lisa, you talked about the mainstream and the necessity to mainstream and the different multiple stresses. One issue I think we haven't yet spoken enough is really to look on what is all going on land in the different industrial sectors, particularly as well in the agricultural sector. And that, of course, is very complicated because of the socioeconomic consequences, if we really want to engage in a discussion about that.
Go ahead, Torsten.
Yeah.
Thank you.
So that is really interesting what Siggy said then, actually, and that's also this idea that agricultural sector is a if you think from a perspective, then that also provides a lever for actually fixing part of a problem. So don't dismiss this and only go for the climate effects on oxygen budgets, but consider also nitrate input. The other thing I would like to say is that I very consciously went through the phase of oxygen ocean acidification, right, here we go, which came up as almost as a wave, received a lot of attention, and yeah, I would say a bit of a hype, a lot of funding, but it also collapsed relatively quickly, I would say, and now we look at it as a factor in a multi-pressure system of climate or greenhouse gas related pressures. And I wonder whether we can shortcut with deoxygenation, or whether we can shortcut this the wave and immediately go to an integrated approach of oxygen into, I would say again, greenhouse gas and climate related topics, rather than probably putting it into a pot with everything, but in the context of climate and greenhouse gas related topics.
Okay, Irene.
Thank you. I think that here certainly we have things that we cannot control and that those that we can. So those that we can control, we should eliminate the cross-cutting nature. So there are different things that, for instance, in the Black Sea Commission, the climate change, which was never introduced 30 years ago, it was not a single group that would agree to deal with that, because it has a really cross-cutting issue, and all our 6 groups are covering this issue to a certain extent. So this turned to be a problem for us, because none of the group took responsibility over that. We also sometimes we are having sometimes also issues between the shipping activities and, for instance, the MPAs. So of course there are many issues that would always be on the agenda, and scientists would never find a common, I hope they would find some common solution. So I would repeat myself, in order to create a synergy which we need to create, we basically need the harmonization. That's again, I'm saying it for the third time today, but I think it's very important. We also need to avoid the gaps and overlaps, because again, all of us are dealing with these issues, and this, to my opinion, would create the synergy that is actually the answer to the question, what is needed, to fight with all these challenges that we are facing today. Thank you.
Okay, thank you. Did Julie want to respond?
Yeah.
Did somebody hands up?
Yeah, just quickly, just to build on what some of the others say, I think communicating it in a multi-stressors approach, where it's one among many of these litany of ocean problems that's caused by the fossil fuel folly and related enterprises. I think that really masks what could be a more direct communication strategy, because in reality, the deoxygenation is impacting the fundamental life support of the planet. And as such, I think it really needs to be elevated in how humanity conceives of it and addresses it. You know, all we have to do is look to some of the more recent studies that you all have contributed, including Curtis Deutsch's paper in Science the other week about the extinction level impacts that this could cause. So I just wanted to put that out there. I think you all have incredible capacity on the science side to develop the research, and would enjoy working with you on how to help communicate to a wider community really the urgency and importance of this particular issue, and not just as a multi-stressor spectrum problem.
Thank you. So there was a question. Did you have a question all the way back there, or were you just stretching? I think there was. Did you have a question back there or no? No. Okay. I just saw somebody waving their hand. Okay.
Is it on? Okay. I have a question for Julie. In interacting with policymakers, you know, we meet with staffers or we provide policy briefs. What are the deliverables, with the contrast in deliverables when working with private sector companies, and what as scientists can we provide to what you were saying, there's these opportunities to work with companies?
Yeah, thanks for that question. So this is manifesting for a lot of companies in terms of their targets around climate action, as I referenced before. For many of them, the way that they're deploying their capital is in terms of buying up credits in order to meet their offsets. And so there's more appetite for biodiversity credits that extend just beyond the carbon offset side of things. So these are more positive investments in biodiversity. And I think that this community could engage on that, particularly if there's a quantification framework. We've seen the development of the task force on nature-related financial disclosures that follows the TCFD framework, but it's lagging by a couple years. So that's an attempt to quantify and create a framework where companies can make commitments and engage in their quantification of their action toward those targets. So we are seeing some global frameworks. I think that, you know, more direct communication around deoxygenation in particular, and how to value actions that are taken to abate that would have a welcome audience. There's I don't know if this community is aware, but a couple of weeks ago, several companies, including Meta, Shopify, came together to fund an almost $1 billion frontier fund for accelerating the purchase of us. And these types of funding mechanisms, I think, could be stood up pretty readily in relation to the biodiversity aspect. Does that answer your question?
Okay, we can take one more quick one. I want to make sure I have time to go through everybody once more. So, who has a microphone? Whoever has a microphone gets to. You can just.
Sorry.
Yeah.
So it's a really interesting discussion. My question is, I think the discussion is focusing now on the Atlantic, Baltic Seas, Shakespeare Bay, and all that kind of stuff. But why are we only thinking about the Atlantic and not the Pacific and Arabian Sea, and things like that?
Did everybody hear the question? You're going to hold the microphone really close and shout.
Okay. But it's a really interesting discussion. Why is it focusing on the Atlantic? and not, for example, Pacific or Arabian Sea, where we have a real big problem with ocean.
Okay, I think
deoxygenation.
it's a product of where our panelists are from and have their expertise. But the question is, why are we not focusing on the Pacific or the Indian Ocean here? Yeah.
I'll have a go. I think indeed a lot of the people here are from the Atlantic, so that's what we know about. But also, and that kind of brings me back to a point that I wanted to make earlier. I don't really know how much data we have for those areas. So that it might very well be that at least there's a lot more known about the impact of anoxia, hypoxia on the coastal zone, because that's where people fish and that's where people see it. I'm not sure how much we know about, well, I certainly don't, about the Pacific or the Arabian Sea. And I think especially if you go deeper, as we saw this morning, there's just not the data for it. So that might be also one of the reasons.
There might be people here who disagree with you on that, but yeah.
You know, I never thought I would be competing for that, but I think it's impossible to be more anoxic than the Black Sea.
Okay, you know, because we're running out of time, I'm going to close by asking you each in 1 minute to offer one action item or recommendation that you think can be taken now to address some of our oxygen challenges, whichever of the challenges you think is most important. And I'm going to start with Siggy online there.
Okay, two key issues. First of all, the sentence, the ocean is losing its breaths, is a fantastic sentence also to bring to the policymakers, because it makes them curious. It made me curious. So try it out. I think that would work. The second is there is going to be now, the European Union has launched a new framework for cooperation, the EU mission for the oceans, but also the other missions for healthy soils, for climate change, for cities. They all offer really a fantastic opportunity to connect what needs to be connected, to align, to harmonize, and to really drive, I think, the different knowledge gaps forward in view of ensuring a healthy ocean by 2030. Thank you.
Okay, Julie, I'm gonna, thank you. Have you go next, Julie?
Yeah, sure. Just briefly, I think the UN Ocean Decade really provides an opportunity to activate more sectors of the economy, particularly the emerging new blue economy, and to really connect with the wider interest in the oceans and sustaining and supporting the health of the oceans. So I think it's really about reaching into other sectors, even beyond global governance arena.
Thank you. And, you know, maybe the good folks out there taking notes, and we can develop a component of good that does that. Okay, Andrea.
Continuing on what Ziggy said, of course, with the mission, we'll have one key deliverable, which is the European digital twin. So the ambition is to have it by 2024, and this will allow a visualization, I would say, that can be offered not only to scientific, but also mostly to the politician, of what are the problematics, what are the scenarios at the level of the ocean. Nevertheless, these are going to happen if we are going to have the data needed. So one thing that is extremely important and on which we are working, hopefully this year, to launch at European level an initiative on ocean observation. There are different things that are happening at the level of various communities in terms of ocean observation without not too much communicating. So at the end, to resume, we need to work more together.
Okay, thank you. Sheila?
Thanks. I feel like everybody said what I wanted to say, so I'm going to say it in my own way. I think we need two things. We need to communicate better. And when I say that, I'm not talking about talking to each other, because you all speak a language that policymakers don't understand. So you need to find a way to speak to policymakers like you would speak to your grandmother, right? And that's the first thing. And the second thing is, in order to do that well, we need a very well parameterized digital twin, which needs good data. And I think we spoke about how we can make this data available. You guys need to get your databases in a way that you could feed into this digital twin so that you can actually give the messages to the policymakers.
Thank you. Torsten?
Okay. The recommendations I won't repeat is that you might consider submitting or putting in your idea about oxygen topic being important to JPI Oceans. But what I actually am also saying is also about communication. And if you want to make the topic float, be aware, as Sheila was saying, how you message. I was wondering whether deoxygenation, hypoxia, anoxia, whether these are really, really good terms. They're a bit clunky. What I really like is this phrase of the ocean becoming warmer and or acidic and out of breath. And I think that's a great language. What is actually really unhelpful, I find, is a blurring in the debate, and maybe that is more in the science policy sphere than in the scientific one, actually. The blurring coming from the phrase that Lisa, you actually had also on the screen, that half of the oxygen we breathe comes from the ocean. This is not the point.
It's not right.
But really,
it was from a report, not my words.
No,
and
absolutely.
it's not, probably not right.
I know. And but it's communicated often as every second breath we take comes from the ocean. But I think it really confuses people. What is the issue now with oxygen? And it's not that we would suffocate if the ocean wouldn't produce the oxygen.
Thank you. Marina?
Thank you. You know, it's very difficult to brainstorm and fantasize when you already work with policymakers, and it's not so easy, you know, to present them the ideas. And we, let's say, already exhausted many different activities and things, but I just thought, and it could be nice to introduce maybe the new motto, which would be always consider oxygen. So whatever we do, it would be nice to always have it like, it's like we have, you know, for human health, we always say that breathing is very important and oxygen for human health is very important, but we never have these particular considerations when we, you know, provide different activities. So I think this motto could be a very nice thing. I think it could be also introduced by European Commission. Regards to Ziggy, I miss you in the Black Sea region. I think it could be very nice to put it somewhere that always consider oxygen whenever you plan any activity, any project, any initiative. Thank you.
Thank you all very much. Let's give our panelists a big hand. We really appreciate you all taking the time to be with us today. Thank you.
Thank you.
I have tissues and I'm just still not going to look at the screen outside.
Pretty loud. Deoxygenation in ocean will go today and then tomorrow, and there's some great posters. So have a wine and a beer after Kenny Rose's talk today. You could go see those posters. So Jody Rumber comes to us from James Cook University in Australia. She's a fish physiologist focusing on the role of oxygen in fish. She's done some fantastic work and gotten a lot of awards, equal amount of awards for her communication skills. And as you learn from the panelists, communicating to the public about ocean deoxygenation is very important, and Jody's done a great job on that.
Thank you so much. Good afternoon, everyone. Full disclosure, I'm having a very weird allergic reaction. And so it kind of looks like I'm crying. And while I'm very upset about climate change, that's not actually why I'm crying. So anyway, thank you so much for that fantastic introduction. And it's really a great honor to be here giving this keynote and working with the United Nations IOC on global ocean deoxygenation over the past year. It's truly a career dream of mine. And as the title of my talk suggests, further away, am I very loud? How's that, better? Hello, how's that? Okay. As the title of my talk suggests, a huge focus of my research program is investigating how sharks are and will be responding to climate change stressors. So but just to rewind a little bit, my foundation is actually physiology. And so that's the approach that I take with my research. And I'm really grateful that Hans Otto Portner gave such a really nice keynote this morning, and overall his work linking physiology and climate change stressors. I specifically focus on physiological mechanisms, particularly those that are associated with oxygen transport and delivery and the cardiorespiratory system, metabolism, the stress response, and movement, all of these that are key to biological fitness. And all of these form the basis of my PhD research back in Canada a little over a decade ago, where I studied how fish use their blood to transport and deliver oxygen to their tissues, especially how that changes under stress. In fact, these are the oxygen issues that I first started investigating, and I'm still sort of jokingly referred to as a fish or shark vampire. Anyway, during this time, I characterized the mechanism by which the fishes can be up to 50 times more efficient than humans at releasing oxygen from their blood to their tissues, especially under stress. Again, fish are pretty remarkable, way more remarkable than us humans. And the fishes do this by using the primary respiratory pigment in their blood, which is hemoglobin. Pull this away a little bit more. And it's not that different than our hemoglobin and hemoglobin that's found in other humans and organisms on the planet, but just different enough that makes them much more efficient, and rightfully so. We think that this trait has been the key component of the success of the fishes over 400 million years of evolutionary history. And of course, this efficient oxygen transport also has environmental implications as well, which is what led to my career and my position at James Cook University, where I am now. So today I use this physiology and this foundation to identify potential avenues for acclimation and adaptation in the coral reef fishes, including the sharks and their relatives, in the face of environmental stressors, and namely climate change. So because I study oxygen transport and breathing and metabolism, I often refer to the fishes that I investigate as my aquatic athletes. And in fact, I gave a TED talk about this back in 2014. And also many of the metrics that I utilize and the approaches that my team and I take are not unlike those that are used to track performance in human athletes. Now, we haven't quite gotten as sophisticated as an Apple Watch. We humans think of athletes, we probably gravitate much more toward the elite humans, aquatic athletes like Michael Phelps. And if we take body size into account, he's racing at speeds of around 1.4 body lengths per second. But really, we humans are much better athletes on land than in water. And so if we look at sprinter Usain Bolt, he's racing at just over 5 body lengths per second. But really, we humans, we're not that exceptional. On land, the cheetah is 4 times faster than our fastest human, sprinting at 20 body lengths per second. And in the sea, the fastest fish, the sailfish, is much more than 14 times faster than Phelps. But my team soon found out that even the tiniest aquatic athletes had a lot to boast about. And these are the larval reef fishes that, when corrected for body size, are doing just as well. So yes, the fishes are pretty exceptional. But unlike us humans, we're in it for gold medals, money, fame, maybe better looks and fit bodies. The fishes are in the race of their lives, and especially with the stressors that we've been bringing to their sports arenas like climate change. Now, although it's gorgeous here in Belgium, I can probably better discuss what we've been up to if you just join me on a little journey to the Great Barrier Reef in Australia, where I'm based, where I've been doing most of this research. So, wow, yeah, it's a bit of a journey. You can see, we zoom in a little bit. We've got Townsville there, and that's the home of James Cook University, the Great Barrier Reef Marine Park Authority, and the Australian Institute of Marine Sciences. And this 2,300-kilometer stretch of continuous coral reef ecosystem that you can see from space, as well as many of the other coral reef and marine ecosystems in the Indo-Pacific, such as Papua New Guinea and French Polynesia, have been my office, my laboratory, and my inspiration since I started my position at James Cook University in 2011. The other wonderful thing about this group here at the colloquium is that we all understand what's going on with climate change and the changes that the planet's facing in terms of climate change. And so that makes it a little bit easier to communicate about this. In particular, though, the Great Barrier Reef and the coral reefs worldwide are facing some of the most challenging conditions and devastation due to climate change. Due to warming, the Great Barrier Reef has undergone mass coral bleaching 4 times in the past 7 years, and that's affected all but 2% of the 3,000 reefs that make up this ecosystem. And this is only a couple of the recent headlines, one from just a few days ago, actually, but this has been going on since March of 2016. And of course, the reefs are just leave that there so we can all have some tears like I'm having right now. Okay, of the approximately 1,500 or so species of fishes on the Great Barrier Reef, my team and I have really started focusing on the sharks and their relatives, and those that may be in some of the most trouble with climate change stressors, and for an array of reasons. On top of the research that my Katarina Santos, as well as myself, one of my current PhD students, Carolyn Wheeler, and former PhD student who's now a postdoc in Canada, Ian Biokos, we recently compiled all of our work and that of our colleagues, summarizing this for the final chapter in the 3rd edition of the Biology and Sharks of Sharks and Their Relatives. And that should be out about next month, I think. We also published a few key reviews synthesizing the current state of knowledge regarding sharks and climate change stressors. Now, we know that sharks and their relatives are one of the most threatened vertebrate groups on the planet, which is largely due to fisheries exploitation, and this has been well studied. In the most recent assessment by Nick Dolby and team, data show that the number of threatened species is now more than twice what was assessed back in 2014. That was the first global assessment. And the most recent assessment also puts tropical and subtropical coastal species at the most risk, and that's about 3/4 of these species. But the other issue that sharks and their relatives have is that's not helping their resilience is that from an ecological perspective, they are case strategists, meaning that these species are typically long-lived, slow-growing, and have a late age of sexual maturity, with really extreme examples like the Greenland shark that can live to be nearly 500 years old, but can take as long as 150 years to reach sexual maturity. Wow, that's a pretty long time. Sharks and their relatives also have long reproductive cycles and produce a low number of large, high-quality offspring. They also display perhaps one of the most diverse arrays of developmental modes, with at least 10 unique strategies identified, including one that's sort of near and dear to my heart, oviparity, where the embryos develop in an egg and are nourished by the yolk until hatching. For these species as well, temperature can dramatically affect incubation time, ranging from several years in cooler climes to only a few months in the tropics. The wide range of these reproductive modes and all of that's likely contributing to specific differences in their vulnerability to fisheries and to climate change stressors, and especially during these vulnerable life stages and also when adults are reproducing. And especially if adults are requiring 1 to 2 decades at least to reach sexual maturity. That makes it extremely susceptible to population declines, whether it be by fisheries or climate change. Yet when we talk about evolutionary history, the sharks have even a deeper history than even the bony fishes. Sharks and their relatives survived all 5 major mass extinctions over the last 450 million years, making them arguably one of the most successful groups of marine organisms. Modern sharks and their relatives began their evolutionary history during a geological period when oxygen levels were on the rise, beyond current day 21%. And as you can see here on the left y-axis, temperatures were in as you can see on the left y-axis, the oxygen levels, and then temperatures were in a cooling period, and that's along the x-axis, along the bottom, and atmospheric concentrations and aquatic PCO2, you can see on the right y-axis, they were in excess of 4,000 parts per million, which is much higher than, of course, today's alarming levels of about 420. So the evolutionary history of the sharks and their relatives has likely helped to shape a lot of these defining physiological processes and traits that are key to their biological fitness, like respiration and acid-base balance and development and reproduction. And in fact, it was thought that because they had this evolutionary history that was over an array of variable conditions, that they'd probably be pretty resilient to climate change conditions, and made a lot of these studies irrelevant for a while. But it's really important to note that while the extant species, those today, have experienced challenging environmental conditions in their deep evolutionary history, this doesn't necessarily mean that they will tolerate these conditions in the future. And the reality is that we're removing these species at an alarming rate. And that's why fisheries, and faster than populations can recover, we're also changing the conditions of their habitats at a rate that's dramatically outpacing the slow generation times of sharks, and making it really hard for them to adapt and evolve to these conditions. So in order to reliably predict how populations will respond to climate change over the next century, we need to determine their potential to acclimate, their potential to adapt or geographically relocate over this very short time frame. So despite all of that, the first study that holistically considered the vulnerability of sharks and their relatives to climate change stressors was only just in 2010. And that was an ecological risk assessment on the Great Barrier Reef that concluded that freshwater and estuarine species and coastal species were most at risk, but compared to the sheer detriment associated with fisheries, most species were pretty low risk. Yet, significant data deficiencies really precluded a lot of these generalizations. And at that point, the first climate change relevant study hadn't even been done on sharks and their relatives, considering either warming or acidification or deoxygenation. So it hadn't even been published. So that was a big wake-up call. And we know that the research into the effects of climate change on sharks and their relatives is challenging, and that's due to a lot of reasons. Logistics that constrain controlled experiments, the size and the rarity of some species, very challenging field research in some cases, the paucity of genetic information, and limited data availability for modeling, and a lot of inaccurate assumptions. And these assumptions are often just based on the problem that we have these broad generalizations of life history traits that are reason to moderate these species responses to climate change. So the Portugal team and the Australian team performed various meta-analyses to detect the trends and responses to date to the 3 main climate change stressors: warming, acidification, oxygenation, and the combinations thereof across not just physiological trait, but all levels of biological organization, spanning molecular to whole organism and ecosystem levels. We organize species by climatic regions such as subtropical, tropical, temperate, and boreal, and by taxa, highlighting the major orders amongst the sharks and their relatives that have been investigated, as well as lifestyle, life history stage, whether we're looking at embryos, newborns, juveniles, or adults, but also the reproductive mode. For example, oviparous egg layers versus viviparous live bearers. Oops. It's not easy to do. Should have had wine instead, right? We also were comparing the responses of sharks and their relatives across various treatments from the studies that we examined, and then the overall responses to each stressor was compared across these major categories that we thought might give us some distinct trends. So in the interest of time, and because I'm still crying, I won't go into the details with regard to like the search terms and the mixed effect models and how effect sizes were calculated and sensitivity analyses. And I've got a team that are geniuses that worked quite heavily on that. But we gathered data until February of last year. And what was immediately obvious was the lack of studies that were relevant, as you can see here in this table on the right, that were largely focusing about 10 species and only about 30 to 40 studies in total, as well as the sheer lack of studies investigating climate change relevant deoxygenation issues. And the date here is pretty important as well, as a few studies have come out. This is ridiculous, sorry. And I'm really excited to hear Marissa Vidor talk about her work on blue sharks tomorrow and deoxygenation. And whilst hypoxia tolerance in general in sharks has been investigated for decades probably, it's been largely from a very mechanistic perspective, comparative physiology, trying to understand their basic physiology, which we'll hear about from my friend Gudrun a little bit later. But what's definitely clear here is that we have a considerable knowledge gap in terms of climate change relevant deoxygenation research in sharks and their relatives. Right, okay. And as we expanded our searches, we still found the sheer lack of other studies documenting deoxygenation or multiple climate change stressors in combination. As you can see here, these are the figures from our Frontiers paper. And the bulk of the studies, as you can see in yellow, investigate warming in isolation, and then acidification with a few combination studies, but no studies investigating acidification and deoxygenation in combination or the trio. Of the trait categories that have been examined under under ocean warming conditions, studies assessing behavior have been largely on temperate species, whereas the studies investigating cellular and molecular traits and survival have largely been on tropical species. And most of these traits have also been mainly examined in embryonic and neonate life stages, which are in blue and teal in these caterpillar plots here. And obviously that's probably because easy to look at embryos and neonates versus adults. And for nearly all of these traits, with the exception of metabolism, no net effect of ocean warming has been detected across all these studies, life stages, and species combined. And when assessing these traits under ocean acidification conditions, we get a more even distribution between temperate and tropical species, although all studies have been examined on developmental and survival traits under ocean acidification have been on embryonic and neonate stages. Now, when assessing all the studies, life stages, and species combined, known effects of ocean acidification conditions were detected for any trait category. And amongst the studies to date that have examined the combined effects of ocean acidification and warming, those that have examined cellular molecular traits have done so using tropical species, whereas the body condition traits have largely been examined in temperate species. And most studies have only investigated the combined effects of ocean warming and acidification on embryonic and neonate stages. So we're seeing a bit of a trend here. The net effects of combined ocean warming and acidification on the various traits were probably driven by warming, and that's evident in the net effect on metabolic traits as well. No net effects of ocean, Good time for another tissue. So of course, we don't have any deoxygenation studies there. And then we're also not considering that there could be antagonistic interactions between these combined stressors as well. So very much some knowledge gaps highlighted here and areas for further investigation. So if we zoom in a bit and incorporate a few more criteria, as we did with the Frontiers paper, we can see specific traits that stand out that help us interpret some of these trends a little bit easier. And in this table, asterisks are indicating significant impacts. Thank you. I'm a mess, I'm sorry. The asterisks are indicating significant impacts, and the arrows are indicating the direction of effects, with up being stimulation and down being inhibition. And the equal sign is indicating the lack of significant effects, where empty cells are identifying responses that were not assessed due to data deficiencies. One of the most evident insights from the experimental research is that warming will likely represent the most prevalent direct driver for sharks and their relatives, with a consistent effect observed across all of these attributes. And although considerable knowledge gaps still linger, directional effects were relatively well understood. Clear reductions of developmental time and increases in aerobic metabolism, eating, thermal tolerance. Although acidification did induce a considerable overall effect, the responses observed appear to be much more context specific and really difficult to pin down. In fact, there weren't any directional effects overall over all of these biological responses, except for increased buffering, of course, to reestablish acid-base balance. The effects of warming and acidification in combination mostly match those for warming, as I mentioned earlier, although different levels of responses are apparent, and considerable knowledge gaps really do preclude a lot of further assessments. And finally, as you can see, the deoxygenation has mostly been disregarded in experimental research. I think that we've established that theme today as well. Although consequential effects are absolutely expected, and we need to be prioritizing those studies. So, what have we learned so far, and what don't we know? Well, sharks and their relatives are likely to be affected by climate change. And we know that we don't even come close to having data to reliably predict whether they'll be able to move to more favorable conditions or latitudes or habitats. But meta-analysis across a broad range of taxa suggests that the cartilaginous fishes may be some of the least likely to move poleward with warming. But again, the paucity of data really precludes these predictions. And we know that the data that are available are very biased towards certain species and certain life stages, for which my team is very guilty of. I'll leave you there with those cute sharks for a moment. Thank you for the tissue. So we've been working on the small, shallow water egg-laying epaulet shark, which is endemic to the Great Barrier Reef and pictured on the left here, as well as the other small benthic sharks and stingrays since about 2012. And we've been working on newborn stages of various reef shark species, like the and the diversity across the 1,200 or so species of sharks and their relatives, and our experimental limitations are definitely contributing to our inability to broadly predict climate change impacts on sharks. But we have been able to examine all life stages under experimental conditions, and we have closed the life cycle in the laboratory. And in fact, right now we have about 20 eggs that we're expecting to hatch anywhere from today onward. We could have babies right now. We started investigating their tolerance to acidification conditions, and we found that they're extremely robust to, in terms of physiological traits, in terms of behavioral traits, especially those associated with finding food and sheltering. These species like to and very much need to hide. And we also know that they are extremely hypoxia and even anoxia tolerant as well, which makes sense given the coral reefs that they live in that experience diurnal changes in both CO2 and oxygen. Do this one more time. I'm almost done, like literally. Temperature is an issue for this species. It speeds up development. It leads to embryos hatching earlier having used up their yolk faster, they have higher metabolic costs, and they have disrupted coloration patterning. And we've done a lot in terms of high temperature tolerance, preference, and how temperature influences reproduction and their circadian rhythms as well. And we've also been looking at the feeding, the cost of feeding and the cost of digestion. And this is ongoing work for my team. Since about 2013 annually, we're usually in the shark nurseries in French Polynesia, and this was the work that catalyzed my PhysioShark research program, which was has grown dramatically with fantastic students and collaborations. And we aim for newborn shark season, which starts about late September and lasts until about late February every year. We're primarily studying sickle fin lemon sharks and blacktip reef sharks under the premise that they would have to be quite robust physiologically due to the areas that they utilize as nurseries and their inherent challenging conditions like temperature, oxygen, and CO2. And whilst this is a really ideal location, given that we've got 10 reliable nurseries, a distinct time frame, and we can be based both in the field, and we can also work at the French laboratory via our collaborations. French Polynesia is also incredible, given that it's the largest shark sanctuary in the world, 4.8 million square kilometers. And so this allows us to truly focus on the effects of climate change without the main stressor of sharks being fisheries exploitation in their lives. I am almost finished. So climate change will not only make things worse, will make things worse for these sharks. Recovery from exercise is already taking 3 to 9 hours. And some of the sharks that we're investigating, they're not necessarily affected by temperature or CO2 levels that they're currently facing, but levels beyond those conditions, and especially if the sharks are already stressed. We've been looking a lot at exercise, recovery. You know, they can handle the conditions that they're at right now, but anything beyond that is quite a challenge. So I produced an 8-minute documentary with Tom Various and Pacific Media House. It debuted in New York City in 2018, which you can also find via this QR code. And we will continue this research and outreach and communication with these areas of our research. Even though they are small scale on just a few species, they really help us with some of these knowledge gaps that we've identified today. And they are catalyzing a lot more studies and awareness. And we do have some big picture work to do. Because of these paucities in data, it means that we can't integrate some of these interactions with multiple stressors, and we can't with certainty inform management and make conservation decisions regarding sharks and climate change. And so I'm putting together a team, a new PhD student, Sophia Emmons, as well as some familiar faces here, like Rui Rosa, Nick Dolby, Brad Seibel, David Sims, but this is only the very beginning and very much still in the brainstorming session where we know we want to define some of these oxygen stressors in sharks and understanding how they're experiencing coastal hypoxia and deoxygenation, oxygen minimum zones. And we want to integrate how sharks get oxygen into their bodies and all of these key physiological metabolic influences, differences in activity, and start to communicate the urgency of understanding deoxygenation issues for sharks and bring it all to the big picture, do some modeling and mapping available habitat and species shifts with deoxygenation. So we're starting to carve this path forward. So nothing I can do would be possible without my amazing team. So I have a huge thank you there. And I'd also really like to thank the UNESCO IOC GONE group for facilitating this opportunity for me and the Australian Research Council, who's funded most of my work. Thank you very much.
I don't think we have time for questions, but Jody will be around for most of the week, so please meet with her if you can. The next speaker is Anne Salvanes from the University of Bergen, Norway, who's speaking on how and why can West Norwegian silt fjords be useful natural infrastructures for investigating consequences of ocean deoxygenation.
Okay, thank you. Thank you. I hope to convince you that fjords are important places to study and to work during these 50 minutes. So ocean basin, deoxygenation, warming, and also reduced ventilation of the interior, those are linked. But how this impact marine organisms and ecosystems, that's largely unknown. And this is difficult to investigate in open ocean ecosystems, as it requires process studies and repeated observations from the same populations. And in the field, process studies require smaller and more enclosed sites, such as in the West Norwegian fjords. West Norwegian fjords, they host deep water ecosystems that are similar to those that are on the open ocean. We have mesopelagic fish, we have big fish and small fish, and all the similar organisms. How do I? Okay. There are many coastal areas in the world that are deprived from oxygen, and one of them, there's a review paper from last year where 19 case studies were described by Pitcher et al. And one of those sites were the Masfjord and the Bergen fjords on the west coast of Norway. And if you look at the Norwegian coastline, it's very long, from 58 to 71 degrees north, and it's rugged with lots of fjords, and it's also bordering the North Atlantic current. And it's, as you can see here, it's long, and you see all the Atlantic current and the coastal current, and the area where we are focusing on today, I will talk about today, is here on the west coast. And what Norway also have is fixed stations, oceanographic stations, since the 1930s, visited every 2 weeks, and which have measured oceanographic condition like temperature, density, and salinity. And those data demonstrate that the coastal water is warming in the North Atlantic on all depths. But also the fjords are warming. We do have some data also from the fjords. They're also warming, even at 400-meter depth. Fjords are quite deep. So it's about 1 degree the last 30 years, and that's quite a bit. That's quite much over a really short period. And it doesn't show all of it here. And the fjord topography, that will affect the renewal of the basin waters of the fjords. As you may see here, Norway is, oh gee, sorry about that. So here, as you can see here, Norway has mountains under the seawater as well as above the seawater. And those sills, those mountain tops make sills that hinder water exchange, the basin water exchange in the fjords. So it's there is a need of if there's supposed to be water exchange in the deep water, getting more fresh, better oxygenated water, then there is a need that what comes in need to be heavier. And as we have seen, coastal water has been warmer. That means it becomes lighter. And that also means it's increased time between the renewals of the deep basin water, and it's less oxygen in the basin water. And we have a time series here from this fjord. It shows that about 7 to 12 years turnaround before it can turn anoxic, actually. And we have the fjord, Masfjord, where we have been. There was 10 years of stagnant water. It was a renewal just last spring. And that's where we have quite a few data from. So how can we study the effect of oxygen loss then on the marine population? Since it's very difficult to do in the open ocean. We do have the fjords in the open ocean. We have lots of currents. It's deep. There are no borders. In the fjords, you have sort of semi-natural borders. And there we can do process studies. Actually, have been started on recently. This one has shown the depth profiles from the CTD stations. We have that we visited the fjord with students since 2011, collected a lot of data, and you can see here how in the basin bottom have 3 years of very low oxygen before it got a little bit better, and last year it got really good. So we recently got funded for a project for study effect of hypoxia on the mesopelagic and the demersal fish communities. And that project originated from the findings of on this annual student field course. Every year we went. We've been going there for many years now. So, and repeated visits to this fjord. That was what showed us the serendipitous discovery of the very low oxygen. And that was great fun for the students and great fun for us. So our research question from in the project, we call it Hype on Fjordfish. We think that is a good acronym. So those originate from the students' works, and it's based on 10 years ecological and oceanographic time series, net-based sampling, and also otolith records from fish that are getting old. So they're very old. Okay, we have 4 work packages, and we study if the fjord oxygen will influence the vertical distribution of fish, and also issues around what that hypoxia causes darkening of the water masses in the hypoxic water. We look into the metabolism and growth, and we will also look into the microchemistry of the air stones. As you may know, that air stones are fish that turn old, can function as a black box, give signals of microchemistry and of stuff that from birth to death. And here we are very lucky to have collaborations with the expert, Carl Lindberg, to help us to study that. And we also will have a work package on the species composition and feeding relationships between organisms. So every year we take an expedition to the fjords. We have lots of equipment, acoustics, depth stratified trawling, depth stratified plankton sampling, and CTDs, water collection, light collections. And in the fjords, some places we can't trawl on the bottom and seabed anymore on the bottom, and then we use deep traps to collect fish. And if we want to study the vertical migration patterns of deep water fish, we also use long lines that we set horizontally with hooks on fixed places, so we can know what depth they are taking on the fish are caught on. Here are some of the species. It's not a huge diversity in the fjords of Norway, but we definitely have quite a high density of the mesopelagic fish, which are quite hot at the moment, and also some smaller crustaceans, like shrimps, krill, and so on. And the sharks, we have loads of sharks and on the seabed, but also some of them are also migrating off the seabed. And we have grenadiers that can be turned up to 70 years old. So those are the guys we try to use as a black box for previous, to search for previous hypoxic events. Okay, well, here is just how the students work, how they know when they get the piles up of these small fishes. And we are off next week to do the same. Yeah. But in the end, I'm not showing more on anything of the data or results here, but that will be done by preliminary research by on student posters and in a talk that will come tomorrow morning. Okay, thank you. That was it.
time and save time. So how, I forgot, how much has the turnover time slowed down with the warmer coastal water?
I'm not sure about how many years it slowed down, but at the moment it looks like it's between 7 and 12 years. Between if the water is stagnant, it can take between 7 and 12 years until we get a renewal. Yeah, so that's quite long actually, yeah, compared to other places.
Yes, yeah. Lisa?
Thank you. Is there any evidence of aquaculture farms influencing or interacting with the natural hypoxia or the climate change related hypoxia?
It was an aquaculture farm in that fjord, and that was by the government. It was told to be moved outside the sill, and afterwards it started slowly to be better conditions in 2 or 3 years before we got the really big inflow of well oxygenated water last year.
Okay. Any other questions from the virtual people? All right, thank you very much. Our next and our last speaker before our coffee break is Gudrun de Bach. She's from Belgium at the University of Antwerp.
Okay. Yeah. Okay. Thank you. Good afternoon. I'll try to keep in time, so I won't keep you too long from your coffee. Today I'm going to talk a little bit about hypoxic effects on shark. And this is actually going to be a more classical science talk and less of a policy talk. So this is about some experiments that we've done. And mostly I want to stress that you will see that it's important to adjust the parameters that you are measuring to the species that you are looking at. There it goes again. The species that we looked at is the Pacific spiny dogfish, Squalus suclei. For a long time, it was also considered Squalus acanthias, but now it has been re-given its original name. Why is it considered its own species again? Well, in general, they live longer, they prefer colder temperature. And as Jody mentioned before, some of these sharks really have long lifespans. So this species is considered to get up to 100 years old, and they only mature at 25 years. So it's important to estimate the effects of climate change on such species that would take a really long time to recover. They're also ovoviviparous, and the mothers are pregnant for about 2 years before they can have their litter, which can be anything from a few baby sharks to maybe 10 or 15. They're an epibenthic species, so and they're also seen to school, where the mature females are often seen inshore, while the immature and the young are drifting off offshore, like teenagers tend to do. They drift away from you. So we've seen this map before. I'm glad I also put it in, or would feel a bit excluded. Well, if we look at where these hypoxic zones are, and then we look at the distribution area of the Pacific spiny dogfish here for the west coast of the United States and Canada, and in Asia, you definitely see red dots there and here as well. And since they live often in inshore water and near the bottom of the ocean, they would definitely, could definitely experience hypoxia. The Squalus acanthias, the spiny dogfish, then in case people are wondering, is all the rest of these spiny dogfish in any other area. So the good thing about working with shark, if you live in Belgium, is that you get to go to other places. Not that we don't have sharks on our 60-kilometer stretch of coastline, but there's many more in other places in the world. So this research has been done in Bamfield Marine Science Center, which is on the west coast of Vancouver Island. It's my favorite place in the world still, even after going to Maria, where Jody was just talking about the black tip reef sharks. It's a beautiful place. And we go there, oh, sorry. We go there in summer. Now I have to go back. We go there in summer because then the shark tend to come in even more inshore on the sandbanks to hunt and to rest. Here you see one of the spiny dogfish, and these are the boxes we, amongst others, use for respirometry, and if you want to keep them individually. The temperature there is not very climate change like, it's about 12 degrees, but we did want to see how they responded to changing oxygen conditions, and this time we just kept this temperature constant. Hans already indicated that in these metabolic rates, so here you see oxygen consumption rates, and here oxygen saturation with full saturated water to the right and anoxic water to the left. And you see metabolic rates of shark, and you see as the oxygen level in the water drops, the oxygen consumption also drops. And then you can calculate this critical oxygen concentration. This is the point where the shark are no longer able to regulate the oxygen consumption rates. So you see here the drop in oxygen concentrations or oxygen consumption rates is much slower. And then suddenly they cannot manage anymore. The water oxygen levels are too low and their oxygen consumption rates drop as well. And this critical point is also ecologically relevant because normally you find species above in oxygen levels that are above this level. Nevertheless, there's quite a bit of individual variation, and you see here in the red dots, this is one individual that shows a very clear critical oxygen level here, just below 20% saturation, while another one here in blue seems to level off more linearly to the low oxygen levels. So some fish seem to regulate quite well, while others don't. So we wanted to know why this happens and also what the effect is in their blood oxygen levels, for example. So this is a dogfish on the surgery table. He has water flowing through his mouth over his gills with a sedative in it at this point, so he's asleep. And we put in an arterial and a venous catheter in the tail here, and a catheter just through the skin here to measure ventilation rates. And then we put them in the box you saw on the right side. If we look at ventilation rates, we see that the ventilation frequency at least seems to have a similar signature. At least it's at first it doesn't drop, it increases as the oxygen levels go down up to the point very near to the same critical oxygen level where they give up ventilating, it seems. It doesn't pay off anymore, it costs more energy than they would gain by it. So definitely this helps to explain why this critical oxygen concentration is there. If we look at the amplitude, so the size of the breathing movements, we don't see much effect. Although you could also say that some sharks here seem to have no effect at all, while others also seem to take bigger breaths when they're around this critical oxygen level. So what is the effect inside the shark? Since we could take blood samples, we looked at oxygen levels in the blood. So, and here you see oxygen pressure in the arterial blood. And also here you don't really see a peak rate, you see quite a linear decrease in oxygen level with the decreasing water oxygen content. Although I must say that it's slower than you would expect if it was a 1-to-1 ratio. So they are regulating a bit and they keep up their blood oxygen level longer than if they would just follow the concentration in water. There's not so much change in PCO2 levels, maybe a slight increase here, probably because they stop ventilating. And the pH, the arterial blood pH, has a slight but significant drop here, possibly due to carbon dioxide accumulation, but as we will see, also due to lactate accumulation. But again, you can see that some sharks perform a lot better than others and can keep their oxygen levels up to quite low water oxygen content. We looked at anaerobic metabolism as well, because you would expect this to kick in. And yes, indeed, at the lowest oxygen levels, so below the peak rate, we see that we get significant lactate accumulation rates. But elasmobranchs in general, and these dogfish as well, have very peculiar energy metabolisms. Their carbohydrate metabolism is quite normal, so depends on glucose and lactate utilization. But in the muscle and the heart, there is very limited or no fatty acid oxidation. And their main substrate is actually ketone bodies. So you only would rely on that if you're really starved for a long time. But for them, it's a normal metabolite. And we see, for example, beta hydroxybutyrate as in plasma levels transported just as other animals transport glucose, and amino acids are also used at oxidative fuel. In other tissues, there is, they do have this capacity for fatty acid oxidation, so they're more teleos-like, let's say, but they also rely on these ketone bodies and amino acids. And in liver, which is the main lipid storage site, you have this very oily, big livers in shark. We see that there is lipid-fueled ketogenesis, and this sustains the demand for these ketone bodies. So then if you do these experiments with hypoxia, does it suffice to just look at lactate if you want to look at anaerobic metabolism? So that's why we took some samples and did metabolomics, and we did it by using proton spectroscopy, so NMR spectra. And for this experiment, we kept the dogfish at 10 to 11% saturation, so below the peak rate. for 2 hours and sampled, and then for 6 hours and sampled. And then we also let them recover, of course, different dogfish each time for 6 hours. If we looked in the brain, actually, we did not see any change in metabolites as well. And we had tens of metabolites. So yeah, that's good. So their brain did not seem affected by the hypoxia at all, or at least the energy metabolism in the brain. In liver, we saw the classic increase of lactate already after 2 hours, still after 6 hours, and it was recovered after 6 hours recovery. Muscle, same, lactate goes up and then disappears after recovery. In gill, which is of course in closest contact with the hypoxic water, we did see increased lactate, decreased glucose, and also decreased creatine and phosphocreatine. And here, none of them recovered actually after 6 hours. So they seem to be affected to a much larger extent than the internal organs, or maybe they're just not used to deal with low oxygen levels. So this does not seem too bad, does it? However, if we look at other metabolites, we see that in the ketone and fatty acid metabolism, we see acetoacetate appear. It decreased, no recovery after 6 hours recovery. Carnitine, no recovery. Beta hydroxybutyrate, actually no change during the hypoxia, and it only started to decrease after 6 hours recovery. Amino acids, all decreased, no recovery after 6 hours recovery time. Acetate, which plays a regulating role in lipogenesis and protein acetylation, increased and did recover, but trimethylamine oxide and betaine that are used by sharks for osmoregulation increased and no recovery. Oxypurinol, which plays a role in defense against reactive oxygen species, decreased and no recovery either. Gill was affected a lot by in carbohydrate metabolism, and also here we see decreases in glutamate and no recovery at all. One of the amino acids decreased but recovered, and then some others that did not recover. Myo-inositol, involved in osmoregulation amongst others, decreased, no recovery. Phosphocholine, which plays a role in membranes, again, no recovery. Trimethylamino oxide, again, used for osmoregulation, no recovery. So it seems that they actually had carbohydrate metabolism was normal, but amino acid and ketone metabolism was severely affected, did not recover. And this seems to have caused some problems in osmoregulation as well, because we see a lot of metabolites involved in osmoregulation that are changing. For the oxyconformity or oxyregulation, an older study has shown that in dogfish embryos, they can actually switch between regulation and conformity. And it seems that these dogfish, whether they prefer one strategy over the other individually, or whether it's just the way they are, anyway, both strategies seem to be true in the adults as well. We definitely saw hyperventilation to aid in the oxygen regulation, and the carbohydrate metabolism that showed the typical response, and recovered fast. But we also saw a confirmation of the importance of the ketone metabolism and amino acids. And here we saw that they do not recover well. And then the indication for the osmorespiratory compromise, which means that if you have to breathe more, if you hyperventilate, you also have an influence on your ion regulation, because more water passes over these thin gill membranes and you might lose urea trimethylamine oxide, amongst others, or have to work harder to keep your balance. Well, that seems to certainly play a role here as well. And then some extra protective molecules were reduced. So very important to consider your organism that you study and their specific characteristics if you want to measure the effects. Because if you would only have looked at lactate here as an indication of anaerobic metabolism, we would have said they were fine after 6 hours recovery, even after such a severe hypoxia. And I guess that's the main take-home message here. And if you're interested in more of our research, we just had a new research group since the start of this year. So you're very welcome to look at our website.